Are you guys able to hear me clearly?
Yes, sir.
Okay. So in the last class, we had already started with the numericals and we had done some one or two numericals. Let's move ahead. So listen the okay numerically carefully because solving is easy, but everything will be given in English, and that we have to understand it correctly. If we write the wrong data, we are going to get the wrong answer. So a company produces three kinds of products: A, B, and C. The company studied the preference of 1600 consumers for the three products. It was found that product A was liked by 1250, product B was liked by 930, and product C was liked by 1000 people. The product A and B were liked by 650. The product B and C were liked by 610, and the product C and A were liked by 700 consumers. None of the products were liked by 30 consumers. Find the number of consumers who like all the three products and only two of these products. Okay, and that is the reason why when I taught you, okay, intersection, union, difference, and complement, I wrote over there and, or, only, and not. That was the reason why I wrote so that when we read it, we'll try to understand so that we understand that is it telling us to find out intersection or complement or union or difference, what is it telling us to find out? So let's write the company produces three kinds of products A, B, and C. Company studied the preference of 1600 consumers. The number of elements universe was set as 1600 because the survey was done of 1600 consumers. Okay, it was found that 1250 people like the product A. The number of people who like product A is 1250. The product B was liked by 930 people. The number of people liking product B is 930. The product C was liked by 1000. So, number of people liking product C, that is the is 1000. Product A and B were liked by 650. Product A and what does and means? And means intersection. So I write A intersection B. Number of people who like, okay, 930 like C. Product A and B were liked by 650. So A intersection B is 650. Then product B and C were liked by 610. B and C and means intersection. Okay, so B and C, this will become 610. Then product C and A were liked by 700. So C and means intersection. Okay, here's how much 700. Next, none of the products were liked by 30 consumers. Okay, if A, B, and C implies like, none of them like means not. When I say A is like, then A complement means not. So it is not like. So what he's saying is in the question that none of the products were liked by 30 consumers. So he's saying us number of elements who did not like A and B and C. A complement means not like product A. Intersection means and. Did not like product A and B and C. These are how much? 30. Okay, again, none of the products are liked by 30 consumers. It means this. None of the products were liked by 30 consumers. So what we have to find out? Find out the number of consumers who like all the three products. And only two of these products. Just apply your mind and only I am giving you 1 minute. In that 1 minute, let me know what we have to find out. Like all the three products means what? What should I find out? Okay, this understanding is very important. I'm giving you 1 minute, think and let me know. I'll just come in a minute. Take a minute, think and let me know. Yes. So I just give you 1 minute. Did you think? Now tell me what you find out. A number of consumers who like all the three products. It means what? What should I find out? Like all the three products means they like A and B and C. This is what I find out. This is what it means. Okay, all the three products means they like the product A and they like the product B also and they like the product C also. Therefore, what does it mean? It means I have to find out this number of elements in A intersection B intersection. Next, only two products. Only two products means what does it mean? Think and let me know. Only two product means either they have liked A and B and they did not like C. They liked B and C, but they did not like the other one, which means this means you have to find out they like only these two products. Means they like A and they like B, but they did not like the product C. Or which means plus Okay, and when multiplication or means plus or, they liked A, but they did not like B. They also liked C. Means here also they liked two products and they did not like this. Or they did not like product A, but they liked product B and C. Okay, these are the three possible things, right? When he's saying only two of this product means they liked A and B, but they did not like C. Or they liked A and C, but they did not like B. Or they like B and C, but they did not like A. So this is what it means only two of these products. So this is what we will have to find out. We'll have to find out this. Okay. So this type of numericals really we have to think, we have to understand so that we can understand what we have to find out. Once we know what we have to find out, then the solution becomes easy. So how do I find out this? Okay, so we have a formula to remember number of elements in A union B union C can be given as n of A plus n of B plus n of C minus n of A intersection B minus n of A intersection C minus n of B intersection C plus number of elements in A intersection B intersection C. So if you see in the given data, we have this, we have this, we have this. Then we have A intersection B also, we have A intersection C also, we have A intersection C also. This we have to find out. This is what he's saying us to find out, and we don't have this. But for that, he has given us one data out here. If you remember, what is the complement? If we remove a set from a universal set, we get complement of that. So what we have to find out that every. So if you just remember D complement law, if it is A union B the whole complement, how do we write? We write A complement and union becomes intersection B and B complement. Similarly, if it is A intersection B the whole complement, how do we write? We give complement sign separately, union becomes intersection, intersection becomes union. This is how we do, right? If we see this is a similar kind of thing. So if I have something like this on my hand, A complement intersection B complement intersection C complement, then what that it would have been given by De Morgan's law, A union B union C, the whole complement. So I can give this complement saying separately and union becomes intersection. So you don't have to buy the formulas always, you just have to use the logic, and that is what I'm doing over here. Okay. So the given data can be thought of as something like this. Okay. And to this De Morgan's law, if I just write it, this is how I can apply De Morgan's law, and therefore I can say that this given data is nothing but this. What he has given us number of elements is A complement intersection B complement intersection C complement is nothing but number of elements is A union B union C, the whole complement, which is 30. I need to find out the value of this A union B union C, and that can be easily done. Okay, if I remove this set from the universal set, I get the complement. So we know that. Okay, A complement will be nothing but remove it from the. Similarly, I can write this number of elements is A union B union C, the whole complement will be nothing but remove this set from the universal set, that is minus A union B union C. If I minus this set from the universal set, I get its complement. Okay. If I remove this set from the universal set, I get its complement. So that is what I do. Now I know the value of this. Okay, that is how much 30. I know the value of this. This is how much 1600 minus number of elements is A union B union. from here I'll get this 30 goes over, this comes over here. Therefore I'll get number of elements in A union B union C is nothing but 1600 minus 30, so that will be 1570. So now I have this value also, but this is the only value which I don't have. So I'll get that. This is what is asked in the question. Okay. So let's substitute the value in this equation number 1. So I'll substitute value in equation number 1, so I'll get 1570 is equals to n of A. N of A is 1250 plus n of B is 930 plus n of C is 1000 minus A intersection B is 650 minus A intersection C, that is 700 minus B intersection C, that is 610 plus number of elements in A intersection B intersection C. We get this value. So this will become how much? 1250, 930 and 1000. So this will be 0, this is 8, this is 11 and this is 3. So I get 1570 is equals to 3180 minus. This is how much? 650, 610, 700, 0, 6, 12 and 19. That is 1960 plus number of elements in A intersection B intersection C. So 1960 is 3180 minus 1960. This is 0. This is 2. 11 minus 2, that will be 2. Then 2 minus 1, that is 1220. Then at 157 is equal to 1220 plus number of elements in A intersection B intersection C. So this will go over here. I get 1570 minus 1220. That is 0, 5, 3, 350. I get number of elements in A intersection B intersection C is how much? 350. We told us to find out
Sir, board is not
how
clearly visible.
many of the consumers have liked all the products. So out of 1600 people, there are only 350 people who have liked all the 3 products. Okay, who have liked all the 3 products. Next.
Sir, board is not clearly visible.
Sir,
So we have
board
done
is
with the
not
first
visible,
part.
sir.
We told you to find out how many numbers of consumers have liked all the 3 products. Here got there are 350 students, sorry, 350 people who have liked all the 3 products. Now next we have to find out this any of these 2 products. Now everyone do one thing, please take the screenshot of this. I'll not give you time to write it down. Hence, the one thing is take a screenshot of this. Take a screenshot and let me know.
Sir, board is not visible, sir.
I hope everyone is taking the screenshot.
Sir, board is not visible.
Just try it out. Next, I'll just count. Just give me 2 minutes. Just try it out. Have you tried it? Now we know what we have to find out. Only these two products. I hope everyone is taking the screenshot. So we have done the first one. I'm rubbing the board because I very
Sir,
less
board
space
is
on
not
my board.
visible.
I've got the value of n of A intersection B intersection C as 350. So now it's telling us to find out only these two products. So how do we find out this? If you remember, we had a
Sir,
formula A intersection B. I have given you one formula, number of elements in A complement intersection of B. It can be written as n of B minus n of A intersection B. Similarly, number of elements in A intersection B complement. It can be written as n of A minus n of A intersection B. What happened? Board is not visible. Just a minute. For others also it is not visible. Now is the board visible? Is the board visible now? Please reply me in the chat box.
No, sir.
Is the board visible now? Students, please reply me in the chat box. Okay, just give me 1 minute. Let me use my mobile's internet. Just give me 2 minutes. I guess we have an internet issue over here. Give me 2 minutes. Now let me know, is the board clear now? Now are you able to see?
Yes, sir.
yes, sir.
Is the board clear now?
Sir, actually, last
Please
question we
reply me
didn't
in the
write, sir.
chat box. Or still is it blurred? Is the board clear or still is it blurred? Students, please reply. Is the board clear or still is it blurred? Please reply me in the chat box. Is the board clear? See now, if there is an internet problem on your side also, then also it will be blur. If there is an internet problem on my side also, then also it will be blur. But at least it is better than previous, right? Okay. Okay, let's move ahead then. If you just remember, I have written this formula. We have written this as a property. Okay, number of elements in A complement intersection B can be written as n of B minus n of A intersection B. So when I have A complement, I write n of B. And when I am writing number of elements in A intersection B complement, when I have B complement, I write n of A. So the similar thing I do over here when I have to find out, okay, number of elements in A intersection B intersection C complement. So consider this as 1. So if I apply the same formula, so here I used to write if it is A complement, then I used to write B. Now if it is C complement, I write A intersection B minus. And then what I used to write, if it is A intersection B complement, I used to write A intersection B. If I have here A intersection B intersection C complement, I just write number of elements in A intersection B intersection C. Uh, so what was the answer of this? If you remember, yes, that is 350. So therefore, number of elements in A intersection B intersection C complement is number of elements in A intersection B, that is 650, minus A intersection B intersection C, that is 350. That is 300. Similarly, I can write number of elements in A intersection B complement intersection C. So then here I write number of elements in A intersection C. If it is B complement, here I will not write B complement. Minus number of elements in A intersection B intersection C. Therefore, I get number of elements in A intersection B intersection C complement is equal to number of elements in A intersection C is how much? 700. Minus this we have got it as 350. This will be 350. Then number of elements in A complement intersection B intersection C. So now I have A complements, I will not write here A complements, I will just write number of elements in B intersection. You don't have to write this one. Minus number of elements in A intersection B intersection C. That would be B intersection C is 610 minus 350. So 610 minus 350, this is 0, 11 minus 5, that is 6, that will be 260. We get number of elements in A complement intersection B intersection C, that is 260. Now we have to find out how many of the people are there who like at least two products. Okay, how many people are there who have liked at least two products? So I'll substitute the value over here. I have got 300 plus 350 plus 260. So I get 300 plus 350 plus 260. So that is 0, 11, and 9. 910. So out of 1600 consumers, okay, so out of 1600 consumers whose survey was taken, there are 900 consumers who have liked at least two products. Okay, there are 910 consumers out of 610 who have liked at least two products. So I hope you have understood this. So let's go for the next numerical then. Please take a screenshot. Okay, please take a screenshot. Okay, so I guess you guys have taken a screenshot. Let's go for the next numerical now. These word problems are very important because in the exam this becomes a major component because we have to read such a large question, we have to write the data and then we have to solve also. Next question in a survey of in a survey of 100 consumers, 72 like product A and 45 like product B. Find the least and the most number that must have liked product A and B. Okay, see the in a survey of 100 consumers, number of people who like product A are 72. Number of people who have liked product B are 45. Okay, but the number of people surveyed are only 100. Then find least and the most number that must have liked both the products. Find least and most numbers of people who have liked A and B both. You can let me know what should we find out exactly. What should we find out exactly? And that time period you just guys think what we have to find out. मला ते परफेक्ट कॅल्क्युलेटरचा लोगो पाठवा ना. त्या सरांनी मागवला आहे मला माझ्याकडे. Okay, so what is saying find out least and the most number of people who must have liked A and B. I hope you must have understood. See, there are 72 people who are liking product A, there are 45 who are liking B, but only 100. If you see, only 100 were surveyed. So if I add both, okay, 72 and 45, how much I will get? 7 and 117. So it turns out to be 117. But how many people I have surveyed? I have surveyed only 100 people. But if I'm adding and getting 117, what does it mean? It means there may be people who have liked A and B both. And that is why I am getting 117. Because if I am surveying only 100 people, how can I get 117? So this gives us an idea that there are many people who have liked product A also and who have liked product B also, and that is the only reason why we are getting 170. So least we can say it's very easy to find out least. So when I subtract this, I get 17. So there will be at least 17 people. There will be at least 17 people who like A and B both. So minimum possibility that okay is 17, that was easy to find out, just subtract 117, okay, and 100, so we get number of elements in A intersection B. So it's nothing but if you just go with the formula, you just write it as A in B is equals to number of elements in A plus B minus A intersection B. So this turned out to be 117 is equals to, this is turned out to be that this has to be 72 plus 45. If I do this minus 17, then only I will get this 100 over here. It was but obvious that there are 17 people, A intersection B means A and B, who have like product A and B. So I've got this list. Next, I have to find out most numbers. I've got this. Least was very easy to find out. How do I find out most? Any idea? You guys can reply in the chat box also, or you guys can unmute yourself and also let me know. How can we find out most? It is logical, there is no calculation in this numerical, and that is why I've taken. Most number means maximum possible number. Who must have like product A also, like B, and like B also. So it is but obviously minimum of 72 and 45, which is nothing but 47. Why? Because there are 45 people who have like product B. So there can be maximum 45 people who must have like B also and A also. So the moment I take 46, so he must have like A also and not B, because there are only 45 people who have like product B. So maximum possibility of liking both the products is only 45. Okay, 45 like A and B. So maximum possibility is how much? 45. It is only logical, there is no calculation in this number. So least is 17 and most is 45. So I have conducted a survey of 100 people, 72 have liked product A and 45 have liked B. So what is the minimum possibility of liking both the products is 17. So there may be minimum, at least there will be 17 people who have liked product A. There can not be less than 17. Why? Because then I do 72 plus 45, I am getting 117, which is greater than the numbers of consumers, okay, which I have taken the survey of. So there has to be minimum of 17 people who must have liked both the products, and that is why it has turned out to be 170. This is the minimum possibility. And the maximum possibility can be the entire 45 people who have liked B must have also liked A, then only this is the maximum possibility of both liking A and B. Okay, I hope you have understood. This numerical was simple. Just take a screenshot fast. We'll go to the next numerical. I hope you guys have taken the screenshot. Let's go for the next numerical. In a hostel, 25 students take tea, 20 students take coffee, 15 students take milk, 10 students take both tea and coffee, 8 students take both milk and coffee. None of them take tea and milk both, and takes at least one beverage. Find the total number of students in the hostel. So I have to find out total number of students in the hostel, but he has given us in some different manner. And what is saying? There are, okay, let T stands for likes T, or let me write let A is equals to likes T, B is equals to likes coffee, C is equals to likes or takes milk. So in our hostel, 25 students take tea. So N of A is 25. 20 students take coffee. So N of B is 20. 10, 15 students take milk. So N of C is 15. 10 students like both tea and coffee. Tea intersection and coffee. So these are how much? 10. 8 take milk and coffee. There are total 8 who are taking milk and coffee. Okay, milk is C and coffee is B, so D intersection C is 8. None of them take tea and milk both, which means A intersection C is 0. Okay, none of them. That is A intersection C is 0. And everyone take at least one beverage. Find total number of students. So what should we find out in this? Then is saying us to find out total number of students. And what is saying? Everyone takes at least one beverage. Everyone, which means A intersection B intersection C is 1. So number of students taking, okay, one beverage, tea and milk and coffee, at least one. Find out the total students. It means what I should find out. I need to find out A union B union. So let's write the formula. A union B union C is nothing but n of A plus n of B plus n of C plus n of A intersection, sorry, minus n of A intersection B minus n of A intersection C minus n of B intersection C plus number of elements in A intersection B intersection C. Therefore, number of elements in A union B union C is 25 plus 20 plus 15 minus 10 minus 8 plus 0 plus 1. So that becomes 25 plus 20 is 45 plus 15 is 60 minus 18 plus 1. So 60 minus 80, that will be how much? 42. 42 plus 1, so that will be 43. So n of A union B union C is 43. So total number of students in the hostel. Total number of students in the hostel is nothing but how much? 43. Okay, so there are total number of students in the hostel is 43. Okay, it's clear. Please take the screen. Please take the screenshot. Okay, I hope everyone has taken the screenshot. Let's go to the next numerical. There are 260 persons with skin disorder. If 150 had been exposed to chemical A, 74 to chemical B, and 36 to both chemical A and B, find out the number of persons exposed to chemical A but not chemical B, chemical B but not chemical A, chemical A or chemical B. So let's read it once again and try to understand. There are 260 persons with skin disorder. Number of elements in universal set is how much? 260. If 150 are exposed to chemical A, so N of A is 150. And 74 to chemical B. So N of B is 74. And 36 both chemical A and B. So when I say A and B means A intersection B. That are how many? 36. To find out the number of persons exposed to, so what is saying? Number of people, persons A but not B means A, okay, but not B means A and not B. Similarly, B and not A. So B and means intersection, not A means A complement. A or B, which means or means it's union or B. Chemical A or chemical B. Okay, so how can we find out? So he has given us number of elements in A union B. We have to find out and directly have the formula n of A plus n of B minus n of A intersection B. All the things there. N of A is 100, n of B is 74, and this is 36. So I get 150 plus 74, so that will be 4. This will be 12 and 2. 224 minus 36. So I get number of elements in A union B. That is exposed to chemical A or B. 14 minus 6, that will be 8. 11 minus 3, again that will be 8 and 1. So 188. The total number of students who are exposed to chemical A or exposed to chemical B are 188. Next is we have said us to find out exposed to chemical A and not B. So N of A intersection B complement can be written as, if you remember, number of elements in A minus number of elements in A intersection B. N of A, that is how much? 150 minus A intersection B is 36. So that will be how much? 150 minus 36. So that will be 4, that will be 114. So number of students who are exposed to chemical A but are not exposed to chemical B are 114. So total 114 students are exposed to chemical A but they are not exposed to chemical B. Similarly, number of elements in A Okay, complement intersection B. So that can be written as n of B minus n of A intersection B. So that will be 74 minus 36. That will be how much? 74 minus 36. So this will be 8 and this will be 3. So 38. So there are total 38 students who are exposed to chemical B only and not exposed to chemical A. Okay, so there are 38 students who are exposed to chemical B only. They were not exposed to chemical A. At the same time, there are total 114 students, okay, who are exposed to chemical A and they are not exposed to chemical B. And there are total 188 students who are either exposed to chemical A or were exposed to chemical B. Is that clear? Please take the screenshot. Hope everyone has taken the screenshot. So are you guys comfortable with this problem sums? Now a little bit when we have done the 3-4 word problems, you will have to practice. Okay, I am going to the next topic now. That is Cartesian product, which will become the end point of this chapter and the starting point of the next chapter called as relation and functions. Okay. Cartesian product of two sets. What do you mean by Cartesian product? Suppose I have set A as 1, 2, and 3, and I have set B as A, comma B. So Cartesian product is nothing but ordered pair. Understand this word. Ordered means in order, which means suppose after 1 we know, after 1 there will be 2, after 2 that is 3, after 3 there is 4, after 4 there is 5. After 1 there is not 5, after 1 there should be 2 only, after 2 there should be 3 only. So this is the correct order of the numbers. So this is what I mean by order. Okay. So when suppose if the teacher says that everyone comes with your roll number one by one. So what we do? First roll number, then the second roll number will go, then the third roll number will go, then the fourth roll number will go. It will not be random. So that is called as order. So when I say your ordered pair, so some order will be followed, some sequence will be followed. So things will work or the things will be returned only in a particular sequence. This is what the word ordered means. And when I say pair, which means group of two. So I write group of two elements in a particular sequence. So what is the sequence? Who will decide? We will decide. Suppose if I am writing A cross B, which means Cartesian product of A and B. So order I said here. What is the order? First I will write the elements of set A and then I will write the elements of set B. The moment I write A Cartesian product of B, so A 1 comma A, okay, 1 comma B, then 2 comma A, 2 comma B, then 3 comma A, 3 comma B. Okay. So pairs means group of two. Okay, ordered means pair, what kind of pair you have to make. First you have to write element of A and then you have to write the element of B. So all the possible combinations are written. Okay, so you have to write all the possible combinations when I write the Cartesian product. Okay, suppose if I write B cross A, which means again I set the order. This time what is the order? First I'll write the elements of B and then I'll write elements of A. So it will be A comma 1, A comma 2, A comma 3, then B comma 1, B comma 2, B comma 3. So this is Cartesian product of B with A, that is B cross A. So the order was first we have to write the elements of B and then we have to write elements of A. Okay, because I have written B cross A. So first the elements of B and then I have to write elements of A. So I hope you have understood A cross B, B cross A. Now how many elements are there? 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. Does it have to be same? Only the order is changed, so the number of elements have to be same. Let me write one more example. Suppose I have 1, 2, 3, 4. And here I have A and B. The Cartesian product of A is B, that is A cross B will be 1A, 2A, 3A, 4A, then 1B, 2B, 3B, and 4B. Okay. Suppose I have one more A, B, and C. Now if I write A cross C, then I can write 1A, 2A, 3A, 4A, then 1B, 2B, 3B, and 4B. Similarly, I can write 1C, 2C, 3C, and 4C. Now let's count the number of elements. So here I have 6. The number of elements in A cross B. Equals the number of elements in B cross A. B cross 6. If I see in this case the number of elements in A cross B. These are how much? 1, 2, 3, 4, 5, 6, 7, and 8. If I see in this case number of elements in A cross C. These are how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now let's try to find out the general formula finding or writing all the possible combinations that is not possible. If I increase the number of elements in the text, then thinking of the combination and then writing the combination and then counting all the combinations is the wrong thing. Because it is very much possibility that we may forget one of the combinations already. When the combinations are less, then it's good. But when the combinations are more, it's very, very difficult to write all the combinations without forgetting one combination. Hence, we may get the answer wrong. So, like the way we had found out the number of elements in a subset, we can find out here also. So, how many elements can be there in a Cartesian product? So, this can be given by a formula. So, say number of elements in first set are P, and say number of elements in second set are say Q. It's simple, just do P into Q. So you will get number of elements. We see here 3 and 2. 3 into 2, that is 6. So 3 into 2, that is going to give me 6. So yes, we had 6 over here. Then in the second case, number of elements in A were 4 and number of elements in B were 2. So 4 into 2 is going to give us 8. So here we have this 8. And in next case, number of elements in A were 4 and the number of elements in C were 3. So 4 into 3, that is 12. You can see it, yes. We got 12 over here. Board is not clear. Just give me a minute. Just give me a minute. Okay. If the board is blurred, then there must have been some internet issue. Just give me 2 minutes. Yes, the net seems to be working very slow. Okay, there seems to be an internet issue over here. Now I'm getting speed properly. Just give me a minute. Now is the board clear, students? Now is the board clear? Is the board clear now? Please let me know now. Our internet is giving us some 19 Mbps speed. So I think so. Now the board should not be blurred from our side. It is showing me 17, 18.
Clear, sir.
Is the board clear now?
Yes, sir.
Please let me know, students.
Clear, sir.
Okay. Now it is giving proper speed. Now it's giving me a speed of 18 Mbps. Okay, so please everyone take the screenshot of this. So the number of elements in the Cartesian product can be given as P into Q, where P is the number of elements in the first set, whereas Q is the number of elements in the second set. So if you simply multiply the number of elements in first set with the number of elements in the second set, then you will get the total number of elements in a Cartesian product. Now if I say how many number of elements will be there in the first one, okay, first Cartesian product and the second example and the third example.
Number of
So what should
elements
be
in
your
set A
answer? We have already
into
done.
number of elements in set B.
Number of subsets will be nothing but 2 raised to total number of elements. So if I say number of subsets, okay, of Cartesian product of A and B, so that will be nothing but 2 raised to, in this case, how many total elements are there? 6, so 2 raised to 6. So which can also be written as nothing but 2 raised to P into Q. If I say total number of subsets, okay, in a Cartesian product, will be nothing but 2 raised to p plus, p raised to p into q. What is p? Number of elements in set K, and q will be nothing but number of elements in set Q. That will only give me total number of elements in a Cartesian product, and therefore I can just write total number of subsets. Total number of subsets will be p raised 2 raised to p into q. Okay, so it is asked in the exam how many subsets will be there. So we will say 2 raised to p into q. So in this first case, the total number of subsets of this Cartesian product will be 2 raised to 6. Okay, in the second case, the total number of subsets for the Cartesian product will be 2 raised to 8. And in the third case, the total number of subsets for the Cartesian product will be nothing but 2 raised to 12. Is that clear? Is this concept clear to you guys? Cartesian product is the concept of Cartesian product clear? Okay. I guess it seems to be clear to you guys. So now we have completed the chapter sets, and we are going to start with the next chapter called as relations and functions. And the definition of the relation is this itself what I have written. So what is a relation? So any subset of Cartesian product of two sets is a relation. Mathematically, what is the relation? Any subset of Cartesian product of two elements is nothing but a relation. So let me take the example which I have already done in the last case. So two sets were A and B, and I have taken their Cartesian product. So in the Cartesian product I have these elements. A Cartesian product of B. So how many number of subsets are possible? The number of subsets possible are 2 raised to 6. So how many number of relations? 2 raised to 6. So how many numbers of relations I can create is nothing but number of subsets. Why? Because what I said, any subset 2 raised to 6 is a big number. Writing all the relations, writing all the subsets is difficult, but still we can try some of the subsets. So yes, you agree this is a subset of Cartesian product of A and B. Suppose I write this. You will agree, yes, sir, this is also a subset. Let me write one more set. Yes, we can say that this is also a subset of Cartesian product of A and B. You will agree with this also is a subset of Cartesian product of A and B. Like that, how many relations I can make? 2 raised to 6. So 2 raised to 6 is a number, right? So which we have written as 2 raised to 3 into 2 raised to 3 means 8 into 8, that is 64 relations. So how many subsets or how many relations I can make of this? I can make total 64 relations or 64 subsets. Each subset of the Cartesian product of two sets will be called as a relation. Each subset. and therefore I have denoted it by R1, R2, R3, R4 just to give it a notion to our head that it is a relation. Okay, we'll give notion to our head. Okay, what kind of notion we'll give? We'll give a notion that it is a relation when I write R. When I write A, B, C, D, so the general notation in our mind is, because we are just in next chapter, that it is, okay, a set A, B, C, D. So any subset of a Cartesian product will be called as a relation. And we can denote the relation with R1, R2, R3, R4. Okay, so relation can be denoted something like this. And if I want to write this, we write it as something like this: A, R, B. And it will be read as A is related to B. So what is small a and small b? So this was Cartesian product of the two sets. So one set was set A and the other set was set B. So elements of set A are denoted by A, whereas elements of set B are denoted by small b. So when I am writing A over here, it indicates elements of set capital A. When I am writing B over here, it means elements of set B. So the ordered pair was first we had written elements of set A and then we had written elements of set B. Hence in the relation I have written A first and then I have written B. Okay. So A related to B. Let us write as A is related to B. So this is how it can be read, or this is how it can be written. Okay, I hope this definition is clear to you. Please take a screenshot of this. The relation is nothing but any subset of Cartesian product is called as a relation. Now we'll do some interesting numericals also in this chapter, because it is not only mathematics. Okay, in the very first lecture, you students were not there, only one student was there. At that time, I explained that mathematics is not only about numbers. Mathematics is about patterns. It's about relations. Okay, it's about things. It's about fractals. It's not only about numbers. Maths is not only numbers. If you must have seen the sets numericals what we have done, though we associated numbers with them, but you see it was logic that one likes this, the other likes this, the other likes this. So in that we have taken consumers, and the consumers is liking some product, the consumers is liking a mobile, the consumer is liking tea, coffee. Okay, so we have associated logic with that. So when I am saying about relation, it need not be in our mind, okay, that it's only about numbers. So when I am talking relations, it need not mean that only like this. Okay, a son is related to father, a son is related to the mother also. A son is related to relatives also, because the mother and the father, these are also children of some other. So indirectly, the son is related to the grandparents also, and that is why we call them as grandparents. So son's father and mother will be, okay, sister and brother of some other. Hence, son of their brothers and sisters are going to be some relation with this son also, with us also, whom we call as cousins, right? So, this relation and function, what we are going to study, basically the relation part. So, the relation part will not only be applied to the numbers or the Cartesian product or what we have seen over here, it can also be applied to real life problems. So we will see some interesting numericals as we move ahead. We'll see some interesting numericals where we are going to apply some relations and functions kind of thing. Okay. So don't only think it as, sir, only it is a Cartesian product, it is only a mathematical definition. No. Since we're studying in your maths, which is about your syllabus, sir, it is only a mathematical definition. But yes, whatever things we have defined in our life, okay, that this son is related, okay, brothers and sisters are related, the cousins are related, the parents and grandparents are related, okay, there is a friend, so this friend is also kind of a relation, okay, enemy, so enemy is also kind of relation, so that all things can also be studied over here. Okay, that all things can also be studied over here. It does not be only this. So I hope everyone has taken the screenshot. So now we said that relation is the subset of the Cartesian product. So indirectly, in mathematical terms, a relation is nothing but a set only. A relation is nothing but a set only mathematically. Okay. Mathematically, its relation is nothing but a set only, and it is nothing but a subset, which means it is a set only. So, if we go in the set, we have seen five sets. So, hence, that can be directly carried over here also. So, types of relation when I see. So, first I can directly carry out the types of sets we have studied: finite set, infinite set. Okay. Then get studying singleton set, null set. Hence, similar kind of definitions can be carried out over here also. So, finite relation, where the number of elements in the relation will be finite, infinite relation, where the number of relations or the number of elements in the relation are infinite. Then we can have next is a null relation or empty relation. So there we had empty set. So here we can have empty relation also. We can directly carry out those things. Finite relation because there was a finite set. Okay, infinite. Then we can have null or empty relation because there we had an empty set also. Then we can have equivalent relations also. Then we can have okay equal relations also. But apart from that, what we studied in sets, the part of which the null relation or empty relation will be where no relation exists, which means there is no subset, there is no element okay in the relation. So this definition we have just carried forward from there. Apart from that, we are going to study some more relations, some more types. So one is called as an identity relation. So what is an identity relation is every element is related to itself only. This only word is very important. Every element is related to itself only. So suppose if I am to write an example, you can write something like this: 1, 1, 2, 2, 3, 3. Or I can write A, B, B, C, C. That should be itself only. Okay. Every relation where every element of a set is related to itself only. It is not making relation to any other element except for itself. Then such a relation is called as an identity relation. Okay, such a relation is called as an identity relation. Then we have next type of relation. Okay, it's called as reflexive relation. Now pay attention over here. Reflexive relation. Every element is related to itself. See, very important. I've used the word only over here, and that word I'm not using. Suppose I have set A, having the elements 1, 2, and 3. So in that context, if I'm talking, so you can see over here, yes, every element of this set A is related to itself. So it is an identity relation. But here if I write, I can write this is also allowed. See, I've written some extra elements also. 1, 3, 1, 2. I've written some extra elements also. Apart from this, I've written some other elements also. Why? Because I have not written the word only. Here I cannot write this extra element. Why? Because this is only. It should only be related to itself, then it is identity. But if it is related to itself, apart from that, if I am having some extra element also, then it will be called as reflexive. But suppose I write like this. Now, this is not reflexive. Why? Now this is not reflexive. Why? Because my set A, my set was having A was having an element 1, 2, 3. So 1 is related to itself, 2 is related to itself. There should have been 3 also. The relation of 3 also should be there with itself. Why? Because I have written every element. Because in the definition I have written, every element should be related to itself. So, which elements are there in set A? 1, 2, and 3. So, when I say every element, so 1 also should have relation with itself, 2 also should be have relation with itself, 3 also should have relation with itself. If I see that 1 and 2 are having relation with itself, but this term is missing over there. Hence, I will say that this example, this is not reflexive. Okay, so I hope you have understood, okay, between reflexive and identity. So, therefore, I can say, I get one very important statement which I can make out with is every reflexive relation is not identity relation, but every identity relation is a reflexive relation. Very important conclusion I can make it out, which is a very important statement because when it comes in exams, it comes in this kind of way. Okay, and they try to confuse you. See, I can say this is also reflexive, this is also reflexive, because by definition it says that every element should have relation with itself. It is not using the word only. It is just saying every element should have relation with itself. So, here when I wrote the relation, I am taking the set in my mind as 1, 2, and 3. And then I have written a relation. So when I say every element should be related to itself. Which means I should have 1, 1, 2, 2 and 3, 3. And others will also be welcome. Here others will not be welcome because of this word only. So this is already there here. This I can say this is identity relation. Which is here. But this is my reflexive and I cannot include 1 and 3, 1, 3 and 1, 2 here. Hence I can say that every identity is reflexive, but every reflexive cannot be an identity relation. Okay, very important statement, understand this. Every identity relation is a reflexive relation, but every reflexive relation cannot be an identity relation. I hope you have understood what do I mean by reflexive relation. Now let's see next type of relation. Let's see next type of relation. Fifth type of relation is symmetric relation. So what it says that if A is related to B, then B also should be related to A. Which means if A comma B element is there, then B comma A element should also be there. Say for example, if I write something like this. If you pay attention over here, here I have 1, 2, so I have 2, 1 also. Which means that AB, then I have BA also. If I am having 1, 3, I am having 3, 1 also. If I am having 3, 2, I am having 2, 3 also. So if I have A to B relation, then I should have relation from B to A also. Okay, the reverse should be there. If 1 and 2 is there, then its reverse 2 and 1 should also be there. If 1 and 3 is there, then its reverse 3 and 1 should also be present. If 3 and 2 is there, then its reverse 2 and 3 should also be present in the same set. Then this given relation will be called as symmetric relation. Okay, I hope it's clear. Let us see one more example. 1, 1, 1, 2, 2, 3, 2, 1, 3. So now reverse of 1, 1 will be 1, 1 only, which is already present. So no need to write 1, 1 again because we know that each element can be repeated only once. Next, I have 1, 2, so I have 2, 1 also. I have 2, 3, so I have 3, 2 also. So this is also my symmetric relation. Let me give one more example. Now, look and say me, is this a symmetric relation? Is this a symmetric relation? 1, 1, if it is having its pair 1, 1 and 1, 1 only. 1, 2. If it is having its pair, yes, 2, 1 is there. 1, 3. It is having its pair as 3, 1. But 3, 2. So there should have been element 2, 3, which is not there. Because it says if A is related to B, then B related to A, which means its reverse element should also be there. So I have written 3, 2, so there should be 2, 3 also. But here 2, 3 element is not there. Hence, I will say that this relation is not symmetric. this relation is not symmetric. Okay? Because there should be element 2, 3, which is not there. 3 is there, so there should be 2, 3 also, it's not there. So this is not symmetric. So I hope you have understood. But if I write an identity relation, so 1 1 reverse is also 1 1 which is present. 2 2 reverse is 2 2 that is also present. 3 3 reverse will be 3 3 only. So this is also symmetric. So the way I said, every identity relation is a reflexive relation. Every identity relation is a reflexive relation. Similarly, I can say every identity relation is a symmetric relation also. Therefore, I can say that every identity relation is a symmetric relation also. But every symmetric relation is not identity relation. But every identity relation is a symmetrical relation. The same statement I said over here also. Every identity relation is a reflexive relation. But every reflexive is not identity. Similarly, I can say that every identity relation is symmetric. But every symmetric is not identity. Okay? Clear? Next. Next is an important one. Try to understand this. Next type is an important one. Taking the same set 1, 2, and 3. For that only I have defined identity, reflexive, and symmetric. And now I'm going to define next. The next type of relation is transitive relation. This is an important one. Try to understand. If A is related to B and if B is related to C, then A is related to C. Okay, it's simple, but the depth of these words is very important. If this and this condition is satisfied, then only you should look for this condition. Otherwise, you should not look for this condition. Okay? Understanding the depth of English words is very important over here. If A is related to B and if B is related to C, then only we will look for A and relation of C. But if A is related to B and there is and B, okay, there is no relation between B and C. If there is a relation between A and B only, then we should not look for the relation with A and C. Only if A is related to B and B is related to C, that is the only time we will look for the relation between A and C. And this is as simple as that. Understanding is A is equal to B and if B is equal to C, then but obviously A is equal to C. Right? A line 1 is parallel to line 2. Line 2 is parallel to line 3. Then I can say my line 1 is parallel to line 2, right? My line 1 is parallel to line 2. Line 2 is parallel to line 3. Again, what obviously say my line 1 is parallel to line 3. So this is a transitive relation. Similarly, A is equals to B, triangle ABC is equals to triangle PQR. And triangle PQR is equal to triangle XYZ. then I can say that my triangle ABC is equal to triangle XYZ. Right? If triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3, then I can say triangle 1 is congruent to triangle 3. So such a relation is called as transitive relation. But if triangle 1 is congruent to triangle 2 and triangle 3 is congruent to triangle 4, then I not go and try to relate triangle 1 with triangle 3 and triangle 1 with triangle 4 because triangle 1 is having relation with only triangle 2. Triangle 3 is having relation with triangle 4. Triangle 2 is not having any relation with 3 or with 4. Hence will not try to relate 1 with 4. Okay. Say for example, you guys are related to Perfect Academy and I am also related to Perfect Academy. Then only there can be a relation between me and you. But I am related to Perfect Academy and you are related to some school. So you are related to school, I am not related to school. There cannot be. But only if I say that I am related to Perfect Academy, you are related to Perfect Academy, and at the same time you are also related to school, then only I can say that I should think of my relation with your school. Otherwise, there should not exist any relation between your school and my school. The only reason I can be related to your school is because of this Perfect Academy. But if there is no Perfect Academy, then there is no relation between me and the school. It is as simple as that. So only if there is a relation between A and B and B and C, we will talk about A and C. But if A is related to B and C is related to D, A is related to B and C is related to D, then I should not talk about relation of A and C because there is no common link. Here I can talk relation between A and C because there is a common link. And who is that common link? Then only I talk about A and C. In this case, I should not even talk about A and C because there is no common link. Here, C and D are different, A and D are different. There is no link between B and C and A and C or B and D or A and D. Then we should not talk about the transitive relations. Got it? So now we have understood if A is parallel to B, B is parallel to C, then A should be parallel to B. If A is congruent to B, B is congruent to C, then A should be congruent to C. Similarly, in terms of numbers, how I can write in terms of numbers? Suppose I am writing 1, 2, 2, 3. So if I am writing 1, 2, 2, 3. So if I am saying A, B, this is B, C. So A is related to B and B is related to C. Then A should be related to C. So I should have this element 1, 2. So now I can say this is a transitive relation. Let me take one more example. So now I have written some more elements, so more combinations. More combinations, so more A's and B's, and you have to think about all of those A's and B's. Now, if this is my A, this is my B, this is my B, this is my C, then there should be A and C which is present. So for these two elements, this is satisfied. Okay. But now I have written one more. So I can take this is A and B. and this I can take B and C. So if it's like that, then I should think about one more combination A and C. So A and C, that will give me 1 comma 1. So this 1 comma 1 should be present over here. So now again I can say this is transitive. But if I write something like this, now this is not transitive. Why? Because see, if this I am taking as A and B and this I am taking as B and C, so there should be a relation between A and C, 1 and 3 which is there. This pair is there. When I am taking this pair, this is my A and B, this is my B and C. So there should be A and C, that should 1 is 1 comma 1, which is not present. Similarly, if I try to group these two, suppose if I try to group these two, if I write like this is A and B, then here I should have B and C. But instead here I am having B and here I am having C. So then we will not talk about relation. It should be A, B and B and C. It should not be like this. Okay, this is what I have written, and that is what I was trying to explain you, the depth of the meaning. Then only I can make two pairs A and B and B and C. Okay, it should not be C and B. I hope you guys are understanding transitive and non-transitive. In very simple language, a relation which can be transferred from one to another is a transitive. See, for example, which I had started in the beginning, I am a son of my parents. My parents are children of their grandparents. So the relation will get transferred. Why? Because they are the son of, so we are also related to them. Because A is related to B. I am A and my parents are B. So A is related to B. My parents are related to their parents. So B is related to C. So A also should be related to C. So that relation got transferred. So this is the transitive relation. Okay, I am son of my father. My father is the son of his father. So his father is my grandfather. So this is the transitive relation. Okay, so this becomes a transitive relation. So I am a son of my father, and there is one more person whose father is my father. So, I am also his son, that fellow is also his son, then there should be a relation between me and that particular one more person. Why? Because the father is same of both. Hence the relation will get transferred, and that relation will now be called as a brother. And this is a transitive relation. And this is a transitive relation. So I hope you are understanding. If the relation can the last type of relation is equivalence relation. So what is an equivalence relation? If a relation is transitive, symmetric, and reflexive, then it is called an equivalence relation. So all at a time, if a relation is symmetric also, transitive also, and reflexive also, all at a time, then Such a relation will be called as an equivalence relation. Say for example, for this I write now reflexive. Every element should be related to itself. So is every element related to itself? Yes. So it is reflexive. Hence it is reflexive. Now symmetric. The reverse should be present. So the reverse of 1 1 is also 1 1. The reverse of 2 2 is also 2 2. The reverse of 3 3 is also 3 3. So it is symmetric. If I write A comma B, then B comma C. So that is one comma something should be there which is not there only. So this is C and D only. So I said only if there is relation, there is B. There is no B element only. So there is no pair only. If there is no pair only, then we should not think of this. Hence, every identity relation is a transitive relation also. Hence, every here we don't have to think between E and C because B and C are not related only. If B and C are not related only, then we don't have to think of this condition only. So each are different pairs. So we don't have to think that this relation is getting transferred or not because each and every individual is different. Say each and every of your classmates will not be related to each other because everyone are having different parents. There is no relation, very less chances of relation will be there between you two. The only relation between you is either you are of the same classes or you are of the same school. That is the only relation you have. Okay. So we don't have to think about transferring the relation at all. So every identity relation will hence be a transitive relation. So it is transitive also. So if a relation is reflexive, symmetric, and transitive, then it is an equivalence relation. Hence, this relation which I have written, okay, as 1 1 2 2 3 3 is an equivalence relation. Why? Because it is reflexive also, symmetric also, and transitive also. Is that clear? So today we started with this relations chapter and we have seen the definition. In the next lecture, we will start with the numericals. Okay? Have a nice day ahead.
Hello. Hello. Kindly leave the meeting.